my solution for number 1 was like not even close to it. I didn't even feel about it. This way it was.
So you'll get a B. I think you'll get a B. What's his grading criteria? Does a B in this one for everybody?
Oh, it's already running. Oh, right here. There we go.
I'm pretty sure you had number 1.
I did not get 100%. No, I did not. No,
But you only got 1 wrong.
All right. So getting back to tracing the program. Okay. So getting back to tracing the program, this time when I run the program, I'm going to check the address of stuff, and I will also show you the one of the registers in the PC in the i386 processor. Yep. Go ahead.
We're having questions about the allocation of memory.
Sure.
When it calls, like a recursive function calls and it has an address, when another function gets called, does it push it out further in memory? Does it like reallocate it to a new?
It reallocates. So basically what happens is when you return from a function, the space that is used on the stack by that invocation is instantly reclaimed. So that same space can now be used again for another function invocation.
But like when you're in the middle of your recursion and like you go all the way down, every time you call a new function, every time you call factorial function, it pushes the last one further out in memory, like higher up.
No, it's the other way around. We start off high and it goes lower.
So then my question is, how does it know where to start?
How does it know where to start?
So it doesn't run into other things, but it does recursion.
It is determined by the operating system. Okay. So that's a very good question. So the question is, how do we know where to start the stack, right? Where to start and where does it end? Okay, and I think those are all related questions.
I think what it really is so much memory is allocated to the execution of that program initially. So it's just like a big chunk of stuff that's available for you that you can just write whatever hell you want in.
Okay, so this is what happens when you run the program. And the best way to illustrate that point, okay, I will get back to this one, but I want to kind of address your question first.
Well, because we could do another step and then recheck the frames, right?
Yes. Okay, well, we can actually go with this one too, I think. Okay, so let's put a breakpoint. We'll list the program, put a breakpoint on the first line of the entire program, run the program. Okay, so we're not really quite at the very beginning of everything, okay? But we can kind of look at, the address of stuff, okay? One register that is particularly useful, these are all the registers, by the way, of the 64-bit version of the processor. I believe I am recording. Yep, it is recording. And this part is also, so we got the audio and also the visual. Okay, so one of the registers, remember the R is really just meaning there are 64-bit versions of the registers. So one of these is particularly useful is the RSP. This is called the stack pointer. The stack pointer is basically indicating the location where this is the last byte, the location of the last byte that is used on the stack. Okay, so if you look at the stack as a contiguous piece of memory, okay, I'm going to use a spreadsheet to emulate that effect. Okay, so I'm going to use a spreadsheet here. And start a new one. Go. So if I use a spreadsheet here, and this is high memory address and these are low memory address. So in this case, according to this program, allocation of the entire stack is most likely starting at location 8 and then followed by all zeros. Okay, that's basically the bottom of the, or I should say the top of the area that is reserved for stack purposes. Okay, is that okay? But the stack pointer currently is at location E240, which means we have used up about, not quite 4 kilobytes, but close to, no, it's more than 4 kilobytes. So some chunk of memory is already used, and that's because when you are in a C program, there is a whole bunch of stuff happening before main even gets controlled. Okay, and all that stuff, uses up some extra stack space as well. But from what it looks like right now, the top end of the memory chunk that is reserved for stack is 8 followed by all zeros in this case. Okay? But the stack pointer is basically a bookmark to indicate what is the last location on the stack that is being used.
And how does it determine that? How does it determine that point?
Okay. Okay. Let me see if I can understand the question. Are you asking how we get to this, printout, or are you asking how do we maintain the stack pointer?
I'm sort of asking how the stack pointer gets its value.
The stack pointer gets its value initially when your program starts execution from the operating system.
So the operating system just knows where it's
correct.
It says, this is what I'm going to let you do, and you do it right here.
And then there's some randomization here as well, because in order to stop people from using stack overflow exploits, some operating system would actually randomize a little bit of where it starts, just so that we cannot. It's not 100% deterministic. So
and that's so you can't overflow by a specific amount.
Well, it defeats some of the Stack Overflow attempts, but not all of them. So there are still ways to kind of defeat. You guys remember the program that I did in the first 2 weeks or so? Yeah. So that one would still work because I can still kind of hack it to the point where it will still work. But it stops a lot of the hacks that were possible without that feature. Okay, so anyway, since we're in main, we can say, okay, what is the address of X? And we already know the address of X. I think it did not change from last time. Was it 24C before? It wasn't 24C if I remember correctly. It was
21C.
21C. So you can see how it's randomized a little bit. So I think the start address or the very end of the entire stack is randomized. Just so that Stack Overflow exploits cannot just be deterministic and say, okay, I know it's going to be this address. So what we'll do is we'll single step into, this is the first invocation of F. So when you do a BT, it can show you that we have 2 invocations active at this point. The first invocation is the bottom one, which is main, and then we are currently in frame 0, which is when n equals to 3. That's the first invocation of F. So as we single step and call F again, and do a BT, you can see how the current frame is always frame 0. Okay, so frame 0 refers to where we are at this point. Frame 1 refers to the previous one. Frame 2 refers to the one before that. Yep.
So is it going to be the stuff in frame 0 that gets a constant address, or the stuff in the other frames, or is it going to continuously reallocate memory for each one?
It keeps allocating more space. So when I use a spreadsheet to indicate what's happening, so let's just say that this is the top end of the entire stack, okay? So when the stack is empty, the stack pointer points here, okay? So let's just say that this much space is used by main, okay? So the first invocation of F is going to use up whatever is right below that. So this is F with n equals to 3, and then when we call F again, it's going to use up these space right below that. So it will be F n equals to 2, and so on. So when we look at how space is allocated on the stack, it goes like this. It starts off high, and then every single time you call a subroutine, it will just use whatever is right below the current point of use. Just kind of imagine that you have a magical notebook, where you have a bookmark to indicate which part of the notebook is in use, and then beyond that is not used. Is that okay? So every time you call a subroutine, you look at the bookmark and go like, okay, I'm using this notebook up to this point, so you will continue to use more pages, but you have to remember to move the bookmark and say that, okay, now I have used 4 more pages, and stick your bookmark like 4 pages after that. Yep.
So the memory location values are decreasing the further you go?
Yes, the more you do recursion, then the stack pointer will be lower and lower.
If it's decreasing, obviously there's a limit.
Yes, there is a limit.
When would you hit that? Is it possible to hit that limit?
Oh yeah. Do you want to see a program to hit that limit?
Yeah.
The simplest program that can hit that limit, how about that?
Sure.
Okay, let's go ahead and write the program. Yeah, go ahead.
Are the things with the main part of the stack, are those staying the same? Or are we allocating for the 0 stack every time there's a step?
You only allocate when you are invoking or calling a subroutine. And that space is freed when you deallocate or when you return from a call.
So what's in stack 2?
You mean frame 2?
Okay, yeah. What's in frame 2? If we do another step, it becomes frame 3, but the addresses will be the same?
Yes.
Okay.
Yeah, it's just
That's
how we number them is floating depending on how many frames are we away from the frame that we want to refer to. Yep.
You showed us for stock like higher address. Does it show like the stock, like how big is stock?
You mean how much space is available?
Yes.
Well, that's what I'm going to do next. Okay, so I'm detouring a little bit just so that we can write a program.
Lowest address for stock and highest address for
I'll
stock.
call this program black hole because it would just chew up stack space like a black hole. And this is one of the easiest program ever to write because I can just write this. But main is a function. Nobody says I cannot call main from main, right? It's not a loop per se. It is endless recursion because there's no end here. It's unconditional recursion. I'm calling main from main without asking, should I call it first?
Will the compiler let you return main from main?
You can return main from main. That would do it too. So that would make it even kind of more interesting. But it's the same thing. It ends up to be the same thing because in order to finish this return statement, it has to call main. And then you're in main again at the beginning. And then in order to return from that main, it will keep going. Huh?
This will compile?
Well, let's find out, right? One thing I really like about computer science is, for the most part, especially when you're using an emulator, you can try whatever you want, okay? And it won't cause a lot of real-world damage. And that's why I'm not a surgeon.
Because you can't just go,
I wonder what would happen if I cut that instead of that.
If I reroute this software straight to the...
Okay, so black hole. The -G is to include debug information. Otherwise, I won't be able to run the debugger, or at least not symbolically know where I am in the program. So -G is kind of useful. And then black hole.c is the name of the source file. Not a problem.
Wow.
Now, you can say that, but TAC, you did not include all the extra stuff. Okay, we can say warn all, okay? Pedantic. Okay, so this will make it nag really, really a lot, okay? And yet it does not complain about a single thing. It's okay.
That compiler is evil.
No, C is evil. The compiler is innocent.
But isn't the compiler what defines C?
Hmm?
Isn't the compiler the thing that defines what the C language is?
The compiler is what makes it possible. That's the realization of the programming language. The programming language itself is evil. Very evil. Okay, so first of all, let's see what happens when I just run the program by itself without the debugger. Okay, you can probably guess what's going to happen. Segmentation fault, right? When most bad things happen in a program in Linux, it would just say segmentation fault, which is basically saying that you're attempting to use an address that you're not supposed to. Okay, that's all that triggers. That's all that will trigger a segmentation fault, and not surprisingly, that is the case.
That was quick.
Oh yeah. Chewing up the entire stack doesn't take much time. Okay, but let's see what happens when we do this inside the debugger, and that's the reason why we use a debugger. Okay, because you can figure out what is going on here, and it gives you some idea of we're getting a segmentation fault. And it is on line 3 of the program. Well, is that surprising?
Nope.
No, because the entire main function only has one statement. Okay, if there's a segmentation fault happening, it has to be that statement, right? There's nothing else. So what is the purpose of this program then? Well, we can still find out the exact amount of space that we have. Okay? Okay, first of all, I'm kind of scared to use BT because it's going to show you a lot of frames. Okay, but I'm just kind of curious. I got to do this. Oh, it doesn't really do much. Okay, it doesn't show the other frames.
So it's the runtime that ends up being the police here.
Yeah, it's a runtime error, not a compiler error.
This is a runtime error.
So
Yes.
it almost looks like the runtime's like, we're not going to let you do this. Like
No. It did everything that it was supposed to do until it ran out of stack space. Okay? Do you guys remember the stack pointer? The stack pointer always points to the location of the last thing that it allocates, right? So the stack pointer, which is RSP in the case of a 64-bit mode Intel processor, will tell us what is the last location. As it turns out, it is 7FFF blah 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 blah, and it's 7FF000000. Okay? So when you compare this address with what it started off with, approximately, that's the amount of stack space that we have. Okay? So we can say, let's say that, okay, there are several ways to do this. You can say, RSP, there we go. Okay, so we can do a division. Let me do this first. Okay, let me run the program again from the beginning. Put a breakpoint on line 3. Run the program, and print $RSP first. So this is the frame pointer, or this is the stack pointer when I started with this entire program. Okay, this is before I chew up all the space on the stack. The stack is basically quote unquote empty at this point because we only have one single frame of main here. Okay, so as I single step, BT should show. Well, it actually doesn't show multiple frames. That is interesting. That really is interesting. I did not expect that. But when I look at RSP, it does change over time. Okay, you can see how it started off with 50 and now it is already at 10. Okay, so this is $2. Okay, so we'll keep going. In fact, we'll have to delete the only breakpoint in this program. So I delete 1, which is the breakpoint, and continue the execution of the program until it crashes. Then I go print RSP again. And then I say print $3, $2. Is it $2 or $1? I cannot remember. Yeah, $2. So we say print $2 minus $1. This is how we use the dollar thing, because you can refer to something that you have examined earlier by just referring to that particular dollar thing. Okay, so it's kind of handy. Otherwise, you have to copy and paste. You can do the same thing, but this is just a lot handier. Okay, and then press the Enter key. So this is basically the amount of stack space that the kernel has allocated for any user process, and that is approximately what, 8 megabytes. So 8 megabytes is the extent or the amount of space that the stack is allocated.
Yep. Try checking the maximum size of each stack frame.
The maximum size of each stack frame. You mean at runtime or at compile time? Because that should be determined at compile time already.
Yeah, the compiler might warn you, but the stack frame size can be different. So I'm just kind of curious what it is right now. Because in the Linux kernel, depending on how it's set up in each architecture, you can have a maximum stack frame size of like 8 kilobytes or 16 kilobytes. So I'm kind of curious how much memory we can allocate in each stack frame. Right?
On a per frame basis?
Yes.
That I do not know. So you'll probably have to look up, and ask, how much space per frame can you allocate. But you have to remember all your local variables have to go into the stack frame. So if you limit the stack frame, it's one stack frame to only 16 kilobytes, that means you cannot allocate an array of, let's say, 64 kilobytes of characters.
If you try doing that, will the compiler warn you?
The compiler may not know how the kernel itself is compiled. So I don't think the compiler will complain. It's going to be a runtime error. Yep.
So
I just checked the GDB manual. You have to set backtrace past main on to bring out the full backtrace for this program. And then I'll show you. I got like 22 on mine before it crashes.
Okay, so main is special. It doesn't track main itself. It stops.
Main is things that that's the beginning of the program. Don't show anything before that.
I see. Yep. Because normally people don't do stuff like this, so there's no need to backtrace beyond main. But I just decided to be lazy and write the simplest program that would chew up all the stack space. Is that okay so far or not? As far as
GDB just doesn't want to go back past main.
correct. Okay, so next thing is, so what is in a stack frame? That's the next question, okay? How do we know what is in a particular stack frame? So for that, it is best to run the factorial program again, okay, in GDB. And we'll put a breakpoint on line 21 again, run the program. Now we are in the main part, okay? So there's another register that is kind of special. It's called the frame pointer. But it's not called the frame pointer as far as the name is concerned. It is called BP, which is base pointer. Okay, so Intel chose to use some terminology that is not current by today's standard. So if you do an IR BP in this case, it's called it's a frame pointer. The frame pointer is referring to a particular point in the frame that is kind of like a fixed point. So everything else is relative to this point. Okay. So there's stuff before this that is considered a part of the frame. There's stuff after this which is also considered a part of the frame. Are we doing okay so far with this? So we want to be able to see what is before this and what is after this just a little bit so that we can see what is on a particular frame. Is that okay? RBP. Okay. Are we doing okay so far with this one? It is related to the stack pointer, but it's not the stack pointer. It's called the base pointer. Okay, so what we do next is examine. Okay, let me see how to display 64-bit things these days. Giant. Okay, so G is giant, which is 8 bytes. Okay, so we need to display G. All right, so we'll go ahead and take a look at examine. Okay, so X is examine. And with examine, you can specify how many things, starting at what address, and how you want to print those things out. Okay. So in this case, we'll go ahead and print out just 10 things. Okay. Each one is in hexadecimal as a giant. Okay. So I'm looking at chunks of memory in quantities of 8. And I will look at stuff that is starting at RBP, but I want to go back a little bit. Okay, because the frame pointer is not pointing to the beginning of a frame, it's actually pointing to, quote unquote, in the middle of a frame, okay? It's pointing to its own saved value, and then on top of that, the return address, and then on top of that, those would be the parameters. So in this case, I would say minus 24, 32, 40, let's say 40, okay? So we're dumping a chunk of memory from the stack, and some of this is a part of the frame, and it's printing 2 at a time on one line, okay? All right, so we'll take a look at this stuff here and see if we can figure out what is what, okay? So we'll take a look at this one first. What do you think this looks like? It looks like the address of an instruction to me, which is most likely the return instruction. And then it also has some additional stuff here. And those are the parameters to this particular program. Let's see, we did it minus 40, which is 5. Oh, I take it back. I take that back. Because RSP itself is 250. And this is 250. This is the frame pointer itself. That's a 0. This is right before that. And then the other stuff is after that. Okay, we can also find out what is X. Okay, the address of X. The address of X is 24C, And 24C is not aligned here. Okay, it's definitely not. That's why. Okay, so X is a 4-byte integer. It's not a 8-byte integer. Despite using a 64-bit architecture, it's not allocating 8 bytes for that. So things are off a little bit. When we change variable X, which location do you think will change? We already know the address of X is 24C. Okay, let me ask you this question then. Set var X equals to hexadecimal 1, 2, 3, 4. Okay. So how would that impact the area that is already displayed? This is a hard question, okay? There's no doubt this is a hard question. Because we know that 24C is somewhere here. Because this is 228, right? So this will make this one 230. Okay, never mind. This is 24C, this is 238. 240 is here. So 24C is going to be somewhere here. Okay. So I'm going to highlight the block where 24C is located. This is the block where it is located. But this is printed out as a 64-bit number in hexadecimal. By changing a 32-bit integer into 1, 2, 3, 4 in hexadecimal, how would that change the highlighted portion in memory? So you need to, I need to answer one question first, okay? If I don't tell you this, there's no way you can figure out the answer. The Intel processor is what we call a little endian processor, which means in order to store a multi-byte integer, the least significant byte is going to be stored at the lowest address. Let me say that one more time. A little endian processor is one that will store the least significant byte at the lowest address. Okay? So when you look at these locations, 280, this is the one that is actually at location 248. Okay, let me just highlight it using a mouse pointer. That's easier. Okay, so being the least significant byte, this is 248, 249, 24A, 24B. This is 24C. Okay, so that means these bytes are corresponding to local variable X because these 4 bytes start at location 24C. Okay. And by storing hexadecimal 1, 2, 3, 4, where 3, 4 is the least significant byte, so 3, 4 being the least significant byte is going to overwrite this byte, and then 1, 2 will overwrite these 2 bytes, and then these 4 digits are actually overwritten as well, but they're overwritten by zeros again, so they won't be showing any change. So the end result is we should expect these 4 locations to be changed to 1, 2, 3, 4 in hexadecimal. Well, let's double check. And voila. Okay? But that is a crucial piece of information is, how do we store a multi-byte integer in memory when the memory itself is byte addressable? Does everybody see why it is important to understand the ordering of how bytes are stored? Okay, so that's my local variable, X, which means, this location here, what is RBP again? RBP is 250. 250 is here. Okay, this is 246. 250 is referring to this part here. It doesn't do the same thing as in the 32-bit version of the processor, so there are things that are slightly different with this particular one. Any questions about? We good?
It's kind of hard to see where things are at with is it, on the left before the colon, that's just the starting space of everything that we're seeing on a particular line?
It basically means this location is 2.8, this is location 2.9, and so on. Because of the little endian nature, you know, the least significant byte is the one that has the lowest address.
Well, then what's in to the right?
To the right? You mean this one
Yeah.
here? That's just, you know, the rest of this line, because one line can display 16 bytes. This is only accounting for 8 bytes, so the other 8 bytes are here. I'm displaying, you know, bytes by chunks of 8. I'm looking at 8 bytes and say, okay, let's look at this as one 64-bit thing.
I got a Pentium M processor, and it looks like it actually stores the counts opposite from what you just showed. So this would be 9C instead of that one being 9C. It's only left to right instead of right to left.
No, she said it. Yeah, it's still an Intel processor, and all Intel processors are using the same standard little n.
So then maybe I misunderstood.
Okay, so getting back to the frame pointer. Okay, I just realized what my own confusion is. So 250, where's 250? 250 is referring to this location here.
Oh.
Okay, that is 250. How do we know that? Because we have 258, 9, A, B, C, D, E, F. So that will make this one 250. Yep. Huh?
It's 240.
2. No, that's going to be 250. 248 is here. This is 248, 49, 4A, 4B, 4C, 4D, 4E, 4F, and this is going to be 50.
So it loops around backwards?
Correct, because
Yeah,
this is the 64-bit number that is before this 64-bit number. So on one line, it is from, you read it from left to right on a line, but within an item, you read it from left to right, because, but only by bytes of 2, I mean every 2 digits. Yep, so that's why it's a little bit confusing to read this thing.
It's freaking. You can get it. It's understandable, but it's confusing.
Okay, but there's some stuff before the frame pointer. Okay, this is before the frame pointer. This is also before the frame pointer. What do you think is before the frame pointer? Well, okay, first of all, do you think main has any parameters? Okay, there's more stuff, you know, basically the same thing, okay? But the question now is, what is this and what is that? They look like memory addresses to me. They seem to be on the stack, right? Because the stack pointer is within this region here. So what is on the stack? There are hidden parameters to main. Even though I said main has no parameters, it actually has parameters. I just chose not to look at those. Okay. Let's write this program in a slightly different way. Okay, so we'll go to factorial again. That's the binary file. Okay, so main actually has 2 hidden parameters. One is ARGC, and then the other one is ARGV, which is const char hard point ARGV. Those are the hidden parameters. At least these 2. I think the environmental variables is the next one, but I can be wrong about that. But every program starts with these 2. Yep.
Is that like the Java where you start with ARGS?
Yep. Yep. Same thing. Same idea.
What is that?
Well, let's figure out what it is. Okay. That's a good question. Let's figure this out.
Explained it. They're just like
Just look at
into
pass
me.
parameters to the program from the command line.
Yeah,
Do you know what string RG is?
Just the same way you can do parameters for GDB or
String that args. And it's in Java.
Yeah, you grab the
You put it in main.
parameters.
It's part of your main.
Okay.
Why do you need it?
So, I need to set a breakpoint first.
You did it right.
No, I have to set a breakpoint first, otherwise it won't stop.
The
Okay.
args is just like a just label for each.
Okay, put a breakpoint on line 21, and then I run the program with this is some bogus parameters on the command line. Okay, there we go. Okay, so I'm passing some double quoted strings, each one. So I have 1, 2, 3, 4 quoted strings as parameters, and plus the command itself, R. Okay, so we'll figure out what is, what we will see as ARGC and ARGV. Okay, run the program. Nothing seems to be of any problem, but we see something here. We see ARGC to be 5, not 4. And then ARGV to be something blah, 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 okay? So the question now is, what exactly are those things? What do you think?
5 arguments.
5 arguments, but how come there are 5? Because, I only specified 4. 1, 2, 3, 4. Where's the 5th one? The name of the command itself is the 5th one, okay? Now, how do we get to those things? What is the type of ARGV, by the way? It's up here. What is one other way to interpret const star ARGV?
That's an array of characters, right?
It's an array of pointers to characters, which is also known as an array of strings. Which means I should be able to say ARGV in square bracket 0 to refer to the first string, bracket 1 to refer to the second string, and so on. Does that make any sense?
Because don't they? Maybe it's Java, but like command line args and then an array.
Well, in C and C++, it's interchangeable. Whether you use an asterisk or just open and close bracket, they mean exactly the same thing, which is actually both a powerful and useful idea, and also why people end up with lots and lots of problems in C and C++. Because you can use any pointer and say, hey, I don't want to look at this as a pointer anymore. I want to look at this as an array. So it is potentially a bad thing, but I'm not here to judge C and C++. I'm just here to explain what it is. Okay. So the first argument is the name of the executable itself, and then the second one probably you would know what it is, because the second one is really just this is, which is the first thing that I specify as the parameters, and then some bogus parameters on the command line. Okay. So these are always passed to every single program written in C and C++ and in Java as well. But in Java, you don't have ARGC, because in Java, you can find out the length of an array by inquiring that. Okay, but in C, the array does not indicate its own length, and you have to indicate the count in this case. Yep.
So I see how you wrote in the parameters that we have int, ARGC, and ARGV. You said those are hidden parameters, right?
Well, they're quote-unquote hidden because of the way I wrote the first version of this program, of choosing not to consider those parameters.
If you don't consider them, is this still happening behind the scenes?
It's still there. It's just that I don't have a name to refer to those.
The ARGC.
Oh, okay. But so it won't affect the program.
No, it's always there.
Okay.
The only difference between the first and the second revision of the program is whether I choose to interpret that or not.
Could this be a security flaw? Can you crack anything with this, knowing this information?
No, it's not a security flaw. I don't think this will cause any security problem by itself.
Can you overload it? Can you overload the main? Can you overload the args in main?
No, you cannot, because main as a function cannot be overloaded, even if you write it in C++, because it always has, you cannot choose your entry point. There's only one single entry point. when you overload a function in C++, it means those are literally different functions. Overloading, means they are entirely different functions. They just so happen to quote unquote have the same name. Okay, but main cannot be like that because there can only be one main as the entry point of your entire program.
Okay. So if you did overload it, it just wouldn't be an entry point.
If you overload main, I don't know what's going to happen. I think the compiler will complain because the compiler is what needs to know which one is the actual entry point of your entire program. So if you overload main, I think the compiler would complain or choose one that is kind of like a default. Okay, so, but let's go back to the other command that we talked about earlier, which is the, it doesn't remember the commands that we've used earlier. So we have to go back to the other one, 24 xg $, rsrbp minus 24. So minus 24 is fine, that should be good. There we go. Okay. So what we're looking for here is, do we see the count somewhere here? Okay, so here's the 5. Do we see any 5s here? Yep, there's another 5. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the way to determine which 5 we should be looking at is to look at the address of ARGC. And ARGC is at 1EC. 1EC is going to be this 5 here.
How do you know that's what you see? Oh, okay. I see 9, 10.
And we're displaying, a little bit before the frame pointer. So that means the arguments are passed, like they are on the stack. They're just, a little bit before the frame pointer, before RBP. Okay. Which also means, what is right after that, which is this thing here. What do you think this thing might be? Let's take a look at the address of ARGV. Okay. Now the ARGV, the address of ARGV refers to the address of the parameter itself, and that's exactly, well, that's not exactly that, is it? It is the location of this. This is E8, that's E0, so it's one before that. I have to dump a little bit more before that. There we go.
How big is a constant chart?
This is our first parameter. This is ARGC. Let's see. And that's an E8. This is ARGV. This is ARGC. So the parameters are on the stack. Are we doing okay so far with examining what is on the stack? Where's my local variable x? Variable x is at 1C, and that will make it over here. So 1C is, FC is going to be here. So your local variables, your parameters, they are all on the stack. Yep.
Does the stack utilize RAM, or is it like internal processor RAM, or does it use the actual RAM?
This is the actual RAM. The processor only has ROM to store its microcode, and you have no control, no visibility of the microcode from the debugger. From your program perspective, you have no access to the microcode.
What about when you're updating the microcode?
Huh?
What about when you're updating the microcode?
When you're updating the microcode, I think you're going through special instructions, possibly I/O instructions to update it. So it's not exactly going through the address space of RAM to update it. I don't know exactly how that part is done, but I'm suspecting it's not going through RAM space or usual address space.
I think Intel has a driver to update the microcode in the Linux kernel.
Mm-hmm.
So you could probably look at that.
Yep. There'll be some interesting code. If you messed it up, that can be problematic. Hopefully it won't cause a bus spike. So any questions about this? Now this is all relatively new to me because when I teach this class in previous semesters, I was using the 32-bit architecture, which has a different way of arranging things. Okay, that's just a different way of doing things. So if we single step into the subroutine, this is now in F. Okay, so when you look at RBP, do you think the current RBP is going to be less than or greater than the RBP from before? So the one from before is, oh, I didn't print it, I did. Okay. It's 1D0, and the one before is, actually I did not. Well, this is already RBP minus 32, so that means RBP is actually E200. So this is less than that, okay? And that's because the frame pointer, or the RBP, is it's a particular fixed point of a frame when you call a subroutine.
So weird. It's so weird.
Okay, look at it this way. What do you need to do when you call a subroutine? What are the things from the caller's perspective that needs to be done when you call a subroutine?
You gotta get some memory.
Okay, so you're the caller. Okay, so you're supposed to call F in this case. Let me just go back to the code here. So list F. Okay, there we go. So let's say F is the subroutine that I'm calling. When you call F, what do you need to do? You need to give it a parameter. Does that make it right? So in this case, n is a parameter. So the parameter will take up some space on the stack. Then what else do you need to do when you call a subroutine? When the subroutine is all done, it needs to go back to where it was called from. So we need to return. We need to save the return address. So the return address is saved right after this, because when you save the return address, it is also doing the call itself, which is jumping into the subroutine itself. Okay. Then it will do some bookkeeping stuff here, and then the local variable is going to be allocated here. So once again, in this direction is high memory space, the other direction is low memory space. So this will give you an idea of the relative place of where n is compared to where r is. The address of n, which is a parameter, should be higher than the address of r, which is a local variable. And then the return address is somewhere in between. Okay? But this is the logical way of doing things. Let's check with GDB and see if that really is the case or not. Okay? So because we are in F right now, we can say, okay, where is my parameter n? E1b. Where is my local variable r? 1cc. So it's putting the local variable ahead or above the parameter, which doesn't make sense to me. This is not how the 32-bit version of GCC works. So this is new to me. I have no idea how it is organizing the stack space in this case, because the ordering doesn't make sense to me.
I have a 32-bit Intel M, and it does it the way you show on the board.
Yep. But I don't know how it can do this, in a reverse way, because how does it know where to allocate space for the local variables? That's the part that I don't get. Well, let's go ahead and run the 30. Well, do we have enough time today? Probably not. We'll do this on Thursday. Okay, on Thursday I'm going to run it in 32-bit mode, using the virtual machine that we used a long time ago. And we're going to use that to illustrate how a frame is organized in the 32-bit compiler. And meanwhile, I'm going to look into the 64-bit compiler, because this doesn't make sense to me, and I don't like things when it doesn't make sense to me.
Now you know how much your students feel.
Sorry?
So now you know how much your students feel. They don't like things when it doesn't make sense to them.
Well, I just need to look it up, because I don't like it. Yeah, I can kind of look it up. vacation mode.
I need a vacation.
Well, it's coming soon. Final exams are all over by the 15th of December.
It's terrifying.
So we only got 2 weeks. Yep.
I had a question, but it doesn't directly pertain to this.
No, go ahead.
It's actually on here.
Oh, okay. I see. Okay.
It's a programming question.
Okay. So are there any questions about, all of this stuff here? What the stack is? Any questions about the stack? Yep.
So my question, when you start compiling program, so your source code will be on top of stack, with lower memory addressing, and your actually variables and some slices will be on bottom of stack with higher addresses, right? It's kind of, if you flip, because you show high address on top and low on bottom. I just see as line numbers, the low on top and high on bottom.
Well,
So
okay, I think I see what you're saying. Okay, so I can.
I just would like to see how the source code and some variables names and some strings they
Gotcha.
in the stuff.
I understand your question. So in addition to all of this stuff here, we'll throw in a global variable. Okay. So I'm just throwing a global variable just so that we can see how things are organized. Where do we put the global variable? Where do we put the program itself, the code of the program, and stuff like that. So we'll take a look at that. Okay. So GDB fact. Put a breakpoint at main. This is a really cool way to do it. You can just put a breakpoint at the entry point of a subroutine. And okay, well, this is already kind of indicative. This is useful because what it is telling you is main as a function is at the address of 4004EF. Okay, so when you see numbers like that, it is most likely the address of an instruction. If you see this on the stack, mostly than not, it is a return address. Okay, it is remembering where to go back to later on. Okay, so this is really helpful. And then we run the program. And when we run the program, we'll go ahead and look at local variable x. Whoops. We'll take a look at the global variable called the global var. Global var. Okay, so that kind of gives you an idea of where the global variable is located relative to where the code is located, relative to where the stack is located. Is that answering your question? Like which part of...
It's totally different places.
They do not have to be next to each other. They can be completely different.
I thought compiler, they put source code,
Nope.
reserve some stock, and so
Nope.
to make it compile.
As far as the compiler is concerned, things do not need to be contiguous. So as far as the compiler is concerned, there's one chunk of space for code itself. So all the functions, main, all the other subroutines, including stuff from the library, they're all lumped into the code space. Okay, so this is one contiguous space, but it can be anywhere within the 64-bit address space. It has a static local variable or static variable space that is located somewhere else. These would include all the global variables as well as static local variables. And then it has a separate piece, that is the stack. So the stack is entirely different. So in our case, the stacks start at location 7FFFF, FFFFF something. Okay, and then the code space starts at 400000, and then the static space starts at location 6 something. So that's approximately where things are located, but they can be completely different. Like the 32-bit architecture has these addresses completely off. They're not even close to the 64-bit architecture. So all of this stuff is determined not by the compiler, but by the kernel, by the operating system. So when the operating system look at the executable and say, okay, how should I load the executable into the memory of your computer, it can relocate things any way it wants to. Is that Is that answering your
Yes,
question?
that sounds
Okay.
good. I just felt it's like they put together at one memory location, but
Right.
you explained it's maybe spread to like different places.
Yep, go ahead.
I was just gonna say because Linux is open source, right?
Linux is open source.
So we could theoretically find that out for Linux, whereas we might not be able to find that out for Windows.
Correct.
Okay.
Yep. Now you can use X. X can do a lot of things. One of the things which is really helpful that it can do is it can disassemble. In other words, you can use I to specify I want to disassemble instructions. So using this, I can say X/I or 20 instructions at the address of main. So it is disassembling the program. And this is how it calls the subroutine. And the way it sets it up is it puts the argument 3 into register EDI, which is one of the registers, and then it will call the subroutine at F. We can also disassemble F itself and figure out how F does things. So it will push the frame pointer, copy the stack pointer to the frame pointer, subtract 20 from the stack pointer to allocate for the space for the local variables. And it is going to copy EDI into, so this is how it does things. Okay. Well, this is actually a little bit harder to explain compared to the 32-bit architecture, but I know what it's doing. The parameters are being passed by registers. They're not being passed in memory space. Yep. So it depends on the number of arguments that you're passing, because if you're passing more arguments, they cannot fit in all the registers anymore. So then it will have to use up some memory space to do it. But this is an agreement between the caller and the callee. As long as they are consistent, it's all okay.
That sounds kind of like a compiler optimization.
It is an optimization because if you pass arguments through registers, you are reducing the amount of memory access that you need, and as a result, it can go faster.
So even when you compile them without any optimization flags.
This is compiled without any optimization flags. But the way the 64-bit compiler behaves is different from the way the 32-bit compiler behaves. So those two are different. And I can understand why too. Okay, let me show you something side by side. This will help further illustrate the use of registers. Go ahead.
So these are all like legitimate assembly language codes?
Yes, in 64-bit mode. This is a 64-bit mode Intel instruction using the AT&T notation. I don't think I have that folder here, but we'll see. Yeah, I do have it. Okay, excellent.
So are you going to emulate 32-bit?
Yep, I'm running the emulator on the other side. Okay. So, and I'm going to run it side by side so that we can easily compare those two. I'm going to start up one more terminal, SSH-P200 localhost. And is it live? Nope. I think it's just user. There we go. Okay. And we'll go ahead and compile exactly the same program. So that means I have to copy the program to the other side. scp fact.c to user at how things are represented.
Different compilation?
No, I just want to give you a contrast of the number of registers available. And that's one big change between the 32-bit mode and the 64-bit mode. So user at localhost, that should be okay.
Should be done, right?
No, I have to specify the location. There we go. There we go. Okay. So we say gcc-o fact-g fact.c, same thing, gdb fact. Okay. The program is identical. We are still looking at exactly the same program. Run main. All right, so now we can have two things side by side. This is from the 64-bit. This is from the 32-bit. And the one thing I want to do is IR, which is info register. It shows the values of all the registers. And this is the one for the 32-bit. So this is the 64-bit. So the 64-bit mode, it has RAX, RBX, RCX all the way down. And then it has all of these registers, R8, R9, all the way up to R15. And then RIP, which is PC, the program counter itself, E-flags, which is our flags register. And let's switch back to here and see what's happening. And we'll just go ahead and display these two side by side. And you can see a pretty good contrast here.
Wow.
Okay, so what is the first thing that you notice? The R versus the E. Okay, so let's not considering the names of the registers. What do you first do?
There's less of the registers on the right hand side.
Exactly. So where are R8, R9, and so on? They're missing. They do not exist in the 32-bit mode. So that means when you run your processor in 64-bit mode, it is capable of using 8 additional general purpose registers. So question, is it a good thing or is it a bad thing?
That's good.
From the optimization perspective for the compiler, it's a good thing, okay? Because you have more registers to play with. And remember, accessing registers is a whole lot faster than accessing memory. Having additional registers to play with means the compiler has more room for optimization. Because the compiler can look at the flow of your variables and say that, oh, I can see your variable here is being set over here, but it's used here, here, and here, and here. I want to keep it in the register if there are enough registers, right? But if I don't have that many registers, like in the case of the 32-bit mode, then I will change the local variable, store the value back into memory, and then every single time I need to access it, I have to read it from memory. Now, you might argue and say that it might be cached, yes, but even if it's cached, it's still not as fast as being in the register. Yep.
So from a programming standpoint, would that mean that it's optimal to reuse the heck out of particular variables because it'll more likely get optimized into a register?
You can leave the optimization to the compiler. So the compiler, understanding that we have additional registers to play with, will try its best to optimize the use of registers. Now the program that we're dealing with, which is the factorial program, is too simple. So it doesn't really, there's not a whole lot of room to use optimization, especially when it comes to how we can utilize the 8 additional registers. But as your code gets more and more complex, then your compiler can now crank out more higher quality code than by hand using a programmer.
Oh, so you can't even program to make it optimized any more than...
It's getting harder and harder for a human to actually write code that is more efficient than what a compiler can crank out with the optimization turned on. So when your compiler has optimization turned on, the compile time will take longer. So it will take considerably longer for the compiler to actually crank out the object code. But how often do you recompile your operating system? Don't answer that question.
I was just about to.
But most people don't, okay? So most people don't recompile the kernel, which means when you do recompile your kernel, you can turn on optimization. It will take 3 times, 4 times, maybe 10 times longer, but it will, huh? But your kernel will also run a lot faster, and if you don't do it on a regular basis, it's okay to turn on optimization. I have had cases where turning on optimization can run code up to easily 4 times faster. It depends on the structure of the code.
Does the kernel get recompiled?
You can recompile your kernel. You can make changes to the Linux kernel and recompile.
Okay.
There's a lot of stuff you can do with it. Now, the other thing I want to show you here, I know we are running out of time, but it's still important because it shows how the two compilers call functions differently. Okay, so I'm still looking at main in both cases. Okay, so we are looking at the 32-bit version and the 64-bit version here. We don't want to look at everything. I just want you to focus on a few things. Okay, so the few things that we want to look at here is this part here. Okay, this is the actual call to F. So in order to call F in this case, I think the -20 may not be. No, it is a part of it. Okay, so we have to adjust the stack pointer, and then the second instruction is the one that I want to look at. Okay, look at this instruction here. This is immediate, which is a constant. Okay, and the other part, we have this addressing mode in our toy processor as well. How do we call that one? Indirect. And how does it work? Are we copying 3 into the stack pointer?
No.
No, we are copying 3 to
the register pointed to by the stack pointer.
the memory location pointed to by the stack pointer, which means it is a memory operation. Memory operations are expensive. They're slow, they're expensive. Okay? This is the 32-bit version. Let's look at the 64-bit version. The 64-bit version is over here, and the equivalent code to actually perform the call are these. Nope, I take it back. These 2 lines. The adjustment of so these 2 lines are corresponding to the actual call to function F. What do you think is this instruction? Move 3 to EDI without parentheses.
Putting the value of 3 into EDI.
Into the register EDI. So it is not a memory operand, it does not access memory. So the 64-bit version, the code used to perform the call is actually quite a bit more efficient compared to the 32-bit version.
So what are the 2 moves that come directly above that? Because those 2 moves are not in the 32-bit version.
Correct. So these 2 moves here are basically saving something to the stack. The frame pointer is determined once we get past this instruction, after we copy the stack pointer to become the frame pointer. The frame pointer now points to a quote-unquote fixed place on the stack. The next instruction, which is a subtraction, we're subtracting 32 because it's hexadecimal to 0. We're subtracting 32 from the stack pointer to reserve 32 bytes on the stack.
Okay.
Okay. So these 2 instructions that I have highlighted, it's just copying EDI to some place on the stack for safekeeping.
So if you're doing that, doesn't that make that a little bit, because at that point, is it still a memory operation?
Yes, this one is a memory operation, so it's the next one.
So is this compilation a little bit more heavy than the compilation in the 32-bit version overall?
What do you mean by heavy?
In the 32-bit version, we're only moving one thing from RAM to memory, right?
Mm-hmm.
Whereas in the 64-bit program, we're moving 2 things from RAM to memory.
I think this one is just the overhead of the entire function itself.
So it's not all that
So
bad.
if I call F like 20 gazillion times, this is not going to be done 20 gazillion times.
Oh, okay.
So the function call, the actual code for the function call are these 2 lines to call function F, whereas in the other one, the actual code to call F will consist of these 2 lines.
Is that what that little equals?
Yeah. The equal greater than is indicating the current execution point, which is where I have just stopped. Because remember, we set up a breakpoint. This is where we stopped.
Which shows you that it's calling function. Okay.
So we are about to call the function, and so that's why I know these 2 lines are corresponding to the actual call to function F in the 32-bit version, as opposed to these 2 lines are corresponding to the function call in the 64-bit version. So the 64-bit version, the agreement between the caller and the callee is if it is a simple function call, we'll just use a register to pass the parameter. As opposed to the 33 mode, which always goes through memory to pass the parameter. It is interesting. But this is how, but I really did not, I wasn't able to teach enough of the instruction set in the i386 to kind of tell you guys how this works. You kind of have a general idea of how this works, but not, unfortunately, I don't have enough time to teach the entire instruction set so that you can look at this and go, to know exactly what is happening. This needs to be like a 6-unit class. I have to negotiate with the math department, take 2 units out of each of the calculus class so that we can stack more units to the computer science classes.
I support that.
Huh?
I support that.
Well, we have 5-unit calculus classes, right? Are they 5-unit classes?
Yep.
But if you go to any UC or even CSU, I think the calculus classes are 3 units. So how come our calculus classes are 5 units? Do they have a lab or something?
No, they're just an hour and a half, 3 days a week.
But I don't understand. How come our math, equivalent calculus classes are 2 units more than the equivalent classes at a UC or a CSU?
Probably because the students at the UC or CSU take their math and get destroyed by it. Because they teach the same concepts just in less time.
Right. I'm just thinking from the perspective of the professor. Is it advantageous to have more units, allocated to teaching the same material? And the answer is,
Yeah.
yeah. In fact, we should make this class, like an 8-unit class, but teach exactly the same amount of stuff. Because that's a de facto race for me, right? In fact, this time is not supposed to be instructional time. I'm just using it to kind of dish out more stuff.
Do they pay per unit? Do they pay per unit?
The way we are paid is by quote unquote FTE. 1 FTE is 1 full-time equivalent. Okay, that's FTE. And a lecture class, a 3-unit class that only has lecture, is 0.2 FTE. So if I'm teaching only classes that only have lectures, I would have to teach 5 classes to make up 1 FTE, which is my base pay. If I teach classes with a lab component, the lab component doesn't scale as lecture units, so it's worth less money. So by lecturing during the lab time, I'm actually taking quote unquote a pay cut because I'm paid less for lab hours compared to lecture hours. So, but in math, the 5 units are all lecture hours, right? So as a result, if someone teaches, let's see, 3 units is 0.2, so you need 5 classes. So if you teach 3 calculus classes, that will make up for 1 FTE completely. As opposed to the 3-unit class, you would have to teach 5 classes to make up for 1 FTE.
So the math professors are just making it in.
That may be one of the side effects. I'm just gonna leave it at that, side effect.
My CISP 360 professor from last semester gets like $150,000 a year.
Say it one more time.
My CISP 360 professor from last semester gets like $153,000 per year.
Get what again? Sorry.
$153,000.
$100
salary. Per year.
Okay.
Is that like how many full-time units would you need for that?
Once you get past 1 FTE, okay, I guess I can turn off the recorder at this time. Then I can talk more freely.